Good afternoon, all of you, and I hope everyone is having a wonderful morning today. So, on behalf of MIDAS IT South Korea, I'm Chinmoy Patnaik, and I'll be your host for this session. So, first of all, I would like to welcome all of you and thank you for participating in the free online courses seminars for the geotechnical engineers. So today we will cover the topic that is the comprehensive slope stability analysis and design using FEM. So in terms of the introduction, I'll just briefly go through the course overview, then I'll tell you a brief about GTS NX. So in this course, this is an online certification course in computational geotechnics using the FEM platform MIDAS GTS NX. So we will introduce the salient feature of GTS NX and the uses of FEM method for engineering solutions. And SRM method will be the method used for slope stability analysis. We'll interpret the results, and in the end, all of you who will submit the assignments, you will get the certificates for computational geotechnics from MIDAS Academy. So let's start with what is GTS NX. So GTS NX is a tool that employs the finite element methodology and covers almost all the types of analysis that comes under geotechnical engineering. So in GTS NX, you can do a static analysis like a static linear or a nonlinear static analysis. Then you can go for construction stage analysis where you try to simulate various stages of the construction. You can do the stress analysis, seepage analysis, stress seepage slope coupled analysis, and also the consolidation analysis for each construction stage. So we also have the FEM methodology based consolidation analysis. Then you can do the stress seepage fully coupled or semi-coupled analysis. So in seepage analysis, you can do a transient stage seepage to exhibit rapid drawdown from a dam, or you can also do a constant head test for a dam when you can try to see the phreatic line and the seepage on the downstream side. Or we have the dynamic analysis where you can do the eigenvalue or response spectrum analysis. We have this linear and nonlinear time history analysis. Plus, you can also do a nonlinear time history plus SRM coupled analysis using the dynamic analysis module of GTS NX. And finally, we come to the big topic for today, that is the slope stability analysis. So here you can use three methods: the SRM method or the strength reduction method, or the SAM method, the strength analysis method, or the construction stage slope stability method. So employing all of these, GTS NX can be used to test the slopes of these following application areas. You can use GTS NX to test the slopes of open pit mining. You can look for the global equilibrium or local factor of safety depending on your critical areas. It has also been employed for checking of dam shoulder stability, the deformations, factor of safety. Also, using a coupled analysis, you can determine where to install your piezometers or inclinometers to check for pore pressure readings and also for the deformation readings from the shoulders. And also, GTS settings can be used if you have the accurate ground data to have an early warning systems for landslide prone areas, or otherwise you can use it for highways engineering to check for the stability of cut slopes by applying various loading conditions or reinforcements. So I hope the introductory part was clear for all of you. Now we'll start with the basic theory behind the slope stability analysis. So if you have any questions that are in your mind, I'll request all of you to please keep them reserved, and feel free to ask them towards the end. We will try to cover everyone's question, and will try to provide a easy solution to your issue or any doubt if you have. So, in the theory for slope stability analysis, we will start with basic LEM fundamentals. So, LEM is nothing but liquid limit equilibrium method. I am quite sure most of you are very familiar with it. So, it's just based on the summation of moments, horizontal forces, and vertical forces as zero. but there are some important assumptions. That is, the factor of safety is constant along the slip surface. Every slice has the same FOS, and the factor of safety is defined as the factor by which the soil strength must be reduced. So if we look at the image below, these are the slices and the forces acting on each slice, or the free body diagram of each slice: the vertical forces, the reaction forces, and the moment based forces. So there are various different methods for limit equilibrium. The Bishop's method, that is the oldest one, the Yanbu or the NTNU or the Norwegian method, the Spencer's method, the Morgenstern Price method, and the Sharma method. So all of them give a very good description of factor of safety, provided your assumptions are correct. So all of them will have the same strength as this short analysis time, and the factor of safety is very debatable in the Bishop method, especially when the horizontal force is acting. So if there is a seismic load that is acting on the slope, then Bishop's method cannot be applied. In terms of more sensitive factor of safety or a longer analysis time, the Morgenstern Price and Spencer can give you a very conservative and an accurate result. So next we'll go to the finite element method. So if I provide an overview, it's a very precise analysis method. It maintains the force equilibrium, the compatibility conditions, and uses the constitutive equations for soil and the boundary conditions. It can easily simulate an actual failure mechanism, because nothing is assumed here. Whatever you get is the result of numerical iterations going on, and it will automatically determine the factor of safety and the failure behavior. So you can also do a construction stage analysis where you can check for in situ conditions and the phase conditions for the construction period. Since it is an iterative method, that's why the analysis time is far longer in here as compared to the LEM methods. So briefly, if I try to describe what is the FEM method, if we just concentrate on the diagram, we can see the failure envelope or the failure line. It needs to touch the failure surface. So the reduction that is applied to each iteration is called as the reduction factor. The reduction factor is actually the most sensitive part of the SRM method. The higher it is, then you'll have a smaller analysis time, but the results may or may not be very accurate, and vice versa. So similarly, if it is very small, then the analysis time will be much longer. That is why one needs to be very careful about the R factor. But GTS NX has its own predefined R factor, so the user doesn't need to worry about it. Now, the factor of safety for SRM method is nothing but the original shear strength by the reduced shear strength value. So I hope the theory behind the SRM method, that is very simple. It is clear for all of you. Now we'll proceed directly to the methodology. So we will start with the natural slope design. Our objectives will be to check for the geometric design, the materials and meshing, load and the boundary conditions, and the analysis and results. So this is a very simple overview of the model. So this is just natural slope, and this is the foundation or the pre-existing ground, and the five nails or anchors are applied to reinforce it. So we will activate these if we find that the factor of safety of the natural slope is less than 1.5. In GTS, you can also directly extrude the same model into a 3D model without any hassle, or without having the requirement to open GTS NX again, because GTS NX supports both 2D and 3D in the exact same UI. So when we come to material models, so we have various solid models that are important for geotechnical analysis. So here we have various models like the Drucker-Prager, Hocken-Brown, generalized Hocken-Brown, the Duncan-Chang, Cam Clay, Jardine, modified Morcolumb, the soft soil, the UBC sand for liquefaction, and then we have S clays and PM4 sand. So we basically have all the models for soil as required by the geotechnical engineers and also for research purposes as of now. Apart from that, if you are competent in Fortran, you can also develop your own user supplied material model. So apart from the soil model, we do have various element models that can reflect your structural properties. So we have truss elements, the beam element, the shell or the plate element. Then we have the interfaces. Then we also have this shell interface that is used to simulate the the movement between the construction, the permanent lining and the and the secondary lining for any tunnel. So we also have various links like the rigid link or the elastic link. And for 3D elements, we have something called as gauging shell. So when it comes to meshing, it is nothing but transferring the geometry into a finite element model, and we just need to assign a finite element mesh. So that is where all the calculations take place, and the problem is solved in there. So we will cover all of this in the numerical model. Now we come to the loading and boundary conditions. So for loading in these model that we will display as the demo, we will only use the gravity loading. At the same time, the model that will be given for certification task will also have gravity loading. We will not cover any other loading conditions as of now. And for boundary conditions, we in GTS you can just go to auto boundary conditions. It will apply the roller boundaries on the sides and the fixed boundaries on the bottom. In the analysis method, we just activate the mesh sets, the boundary conditions, the loading conditions, and in solution type, the SRM analysis is good enough for the in situ. So when it comes to results, this is how it's going to look like. So the factor of safety for this particular design that we will cover was less than 1.5. It's 1.4, and the vectors or the arrows are the displacement vectors that show the direction of the slope movement. Since the factor of safety is less than 1.5, that means we're going to need reinforcements. So now we'll go to the reinforced slope design. So here the objectives remains the same. The only addition will be the addition of the soil nails or the anchors, and we will try to see how to make the properties of the soil nails. So the soil nails are placed at the vertical distance of 6 meters each and with a length of 10 meters. So for material properties, we give the properties of steel to the nails, and we model them as embedded truss with a diameter of approximately, let's say, 8 mm. It completely depends on you and your project on how you want to define your structural elements, and it is a very subjective matter. So for our particular model, we have taken a diameter of only 8 mm. So again, with meshing, the same meshing procedure will be followed for both, which we'll cover. And finally, we come to the analysis method and control. So let me interrupt for a second. Uh, if you have any questions, please reserve them and ask them towards the end. We'll be very happy to acknowledge your question. Plus, if you have any problems with any slide, please also note down the slide number so we can directly go over there and address your questions. Thank you very much for your cooperation. So with the analysis method and control, so we have the SRM analysis for two cases, the natural slope condition and the reinforced slope condition. So otherwise, you can also do the construction stage analysis where you, in the first stage, you just simulate the nonlinear static or the in situ conditions. And in the second stage, you apply the reinforcements. So when it comes to results, the factor of safety increases by around a factor of zero point 0.4, and this is how the displacement vectors are going to look like. So this is something that we will try to simulate in the numerical model. And next comes the results on the structural elements. So the truss has an axial load ranging from 19 kilonewtons to 407 kilonewtons. And since they are positive, so they're all tensile forces. And the results, we can export the results directly into Word format or image file based on how you need. You can also export the entire model result into a 3D PDF format, but depending on your computer's hardware capability and the core performance, it might take some time to generate a 3D report, because it's an animated report as seen like this. So now let's go to the numerical model. So what I'm gonna do is I'm gonna open up GTS NX now. So please allow me a couple of seconds. So here we go to this drop down menu, we go to new, and in the project title you can apply your name or whatever it is, and in the model type we choose as 2D and the gravity direction as Y. So please take a note, when you are opening up a 2D model, the default gravity direction will be Y, and if you are opening a 3D model, the default gravity direction will be Z. So this is how you can easily differentiate between the UI, that whether you have opened up a 2D or a 3D model. Now, um, here I'll go back to 2D model and I'll press OK. So this is how my grid will look like. And so at the very first, what I'm gonna do is I'm gonna reduce the grid size first. So the grid size is 20 meter now. I'll bring it down to, let's say, 2 meters. User defined 100. Press OK. So now my grid size has reduced. Now what I do is I go to geometry, and there are two ways of creating the geometry. One is by Jose, yes, you can import a topographic map from CAD 3D. Yes. So if you want to import anything, just go to the drop down menu, go to import. You can have these kind of files, a DWG, a DXF, or a Parasolid, or a CATIA, or an IGS file that you can import. But here, since it's a simple model, we can just draw it right away, and we'll see how it looks like. So now what I'm going to do is just take out this part in here and I'll put it in there, and I just arrange the icons as they are. I go to model. So there are two ways of creating this geometry. One is by points and the other is directly by lines. So I'm not going to cover the points part because that is part of the tutorial. So you can always practice the tutorial in the end. And also in the tutorial, along with the tutorial, will be provided a 15 days trial period for GTS NX. So you can finish your assignments on time and submit them. Now, so I go to this creation of lines, start from the origin, go a bit left, let's say 90 meters. From here to bottom, let's say 50 meters. From here and then to the top. So if I switch off the grid, you can see how it looks like. It looks like this. Now I switch on the grid again. I draw a line from here till here like this. Let's say I have a 50-meter height slope. Then I just create a line like this. Now, if I switch off the grid, you can see our basic slope design is complete now. So after this, what we're gonna do is we're gonna switch on the grid and we will try to draw the points or the lines from where we'll draw the anchors. So I mentioned that the vertical distance between the two nails will be 6 meters. So let's say I draw a line from here to here like this. So each grid is around 5 meters. So like this. So there we have it. We have drawn the lines from where we can draw the anchors. So what we are going to do right now is that we will use the intersect option. So with the intersect option, we just select all the curves in here and we press OK. So what it does is that it removes all the free curves and makes a connection between all the uh, edges that have been drawn based on the tolerance limit that has been set in your model. Then I go to points 1, 2, 3, 4. So we have 4 points in here. So from there we'll draw the anchors. Now there is one more thing that we need to do, that is finish this one up. So I'll draw a line from here till the end. And I'll also use the intersect option to connect this one to this one. I press OK. So now you can see the line has been divided, and I delete this free edge. So from here we will draw the anchors. But before that, what I'm going to do is I'm going to delete the free edges. So we do have the points from where the anchors will be drawn. So I switch on the grid now. Select this. So this is how my anchor will look like. I think the length is a bit longer than 10 meters, so we'll shorten it up. Yes, 28 meters. So we will shorten it up. So what we're going to do is we're going to press undo. Switch on the line again. It's going to look like this. So now what we're going to do is we're just going to copy this line into all the points. So this can be done very easily. Let's go to translate, select target object. We do is that's the 2 points vector, the first point being here, second point being here. Copy this and apply. Similarly, we again select, click in there, we press delete and we select this point, apply. Similarly, we press delete again and we press apply. So it seems to be a minor error in there. So we're just going to redo it again. Select this as the main point. Second point being here. Calculate. Okay. So there we have it, our 4 anchors. Please note that this is not exactly 6 meters in height, because if I switch on the grid and if I just look at the vertical distance, it's 10 meters. So it depends on your model size. They can always change. So you do not need to worry about it. Just follow the instructions that will be given in the tutorial, and that's how you can design your own model. This is the way to design the model, so you don't need to worry. You can use any methodology you want. So I now switch off the grid, and I'll describe the material properties. So for the material properties description, I go to create isotropic. So I go to this model type as more column. Elastic modulus will be kept as 50,000 or 50 MPa. Poisson ratio 0.3, unit weight 20 kilonewtons per cubic meters. Porous is not required because we are not taking water conditions into account. For nonlinear tab, the cohesion will be kept as 1 kPa and the friction angle being 32 degrees. And we name it as soil. And we press apply. Then we go for the foundation. So we again go to general. We enter it as 60 MPa or 60,000 kPa. Poisson ratio of 0.19. Unit weight dry of 19. Porous saturated unit weight of 20. And a cohesion of again 1 kPa. Friction angle of let's say 32 degrees. And we name it as foundation. And I press OK. So now we're going to apply the isotropic conditions or the steel property. So I can go to isotropic, elastic, and name it as steel. The E modulus being 210 or 200 GPa, so it will be 2E9. Poisson ratio of 0.33 and unit weight of 77, and we name it as structure. So we press OK. So there we have it. Our material properties have been defined. Then we go to defining the property for the meshing. So for that, we need to convert the material properties into various section properties like 2D, 3D, or 1D. So start with the 2D property or the plane strain property. So here, what we do is that um, we just write as plane strain, right, as soil, and the material will be soil. We press apply. Similarly, for the foundation, the material property will be foundation. We go for OK. Then we create 1D. Then we go to create the property for the nails. That is the embedded truss property, and I name it as, let's say, nails. So constitutive behavior will be taken from material, and the material property being steel. I go to section, solid round, D being 0.008 meters. Okay. Okay. So there we have it. So it's time to start with the meshing now. So what I do is I go to 2D, go to auto area, put this size as 1 meters, and I select the edges on the front or on the top, and I choose the property as soil, name it as soil. press apply. So what happens now is that we are getting an error that there are some duplicated edges. So we'll see which edge has been duplicated. So what I do right now is, if I hide this one, and I go to here, and I again press 2D auto area, and I select the edges manually. So, and I press 1, property being soil, soil, apply. So this is how it looks like. Similarly, for the foundation, I select the edges on the bottom, select as foundation, and name it as foundation, size being 1, and I press apply. So after the meshing has been complete, one has to check if the nodal points are connected properly or not. So if you zoom in, you can see that all the lines are straight and continuous. So that is an indication that the nodal match is perfect. So after that has been done, we leave it, and then we go to mesh, then we extract the elements. So we're going to extract the 1D elements to create the nail mesh set. I select the 4 curves in here, and I press OK. So if I switch off the foundation and soil, you can see the nails mesh set, the foundation, and the upper soil body. So next comes the part of aligning the element coordinates. So for that, if you can look closely where the cursor is moving, you can see the Y is on vertical direction, X on the horizontal, and Z is also on the lateral direction. That is, Z is on the longitudinal direction. So this is how our element coordinates should look like. So now if I switch on the element coordinates, you can see it is not exactly the case. Some are along how they should be, and some are not. So for that, it's actually very easy doing it. So what we do is we go to mesh element parameters, go to 2D, change CSS, select all the elements, and here choose the base element. So for the base element, just choose the element that has the proper orientation that you need. So I choose this element, and I press OK. So now you see all the elements have the same exact orientation as the global orientation. Now, after this, we'll do the same with the nails. You can see it's not correct. So again, go to parameters, go to 1D, change CSS, select all. First, I'll align them with the neighboring 2D element, and I press apply. Then this is the vertical direction. So what we need to do is we again select the objects. Then we select the 1D base element as this one. We press OK. So there it is. Our nails have been also organized. So our meshing part is complete now. So I switch off the element coordinate systems. So now what we are going to do is we're going to define the loading conditions and the boundary conditions. So with the loading condition, we just go to self weight. We name it as SW, and we press OK. So this red downwards indicating arrow means it has been activated. Go to constraints, auto, and name it as ground, and we press OK. So roller bound is on the side, fixed bound is on the bottom. So this is how the finite element model is being created. So the steps being geometry, materials, meshing, loading, boundary conditions, then analysis. Well, it's also very subjective. You can also create the material properties before building the geometry. It completely depends on how you want to try it. So next we'll go to creating the analysis cases. So I'll just go to analysis, and I go to general, and I name the solution as SRM. The first being uh, natural slope, and I just activate the foundations and the soil boundary condition, the loading condition, and I press apply. Second will be the reinforced slope. So I here activate the nails and I press OK. So if I go to analysis, now we have two analysis cases. Similarly, if you want, you can also create a third analysis case, that is the construction stage case that I mentioned before. So I go to either stage set. You can just click on it and right click and then add construction set. We press, we name it as slope. Then we press add slope. Then we go to define construction stage. Our model is on the right. So in the bottom, you can see the show data option. Just click activate in here. So right now you can see there is nothing that is activated. So for the first stage, we name it as natural, or let's say in situ. So that will be your natural state. So here it will be a non-linear static plus SRM analysis. Activate the foundation, the topsoil, ground, or the boundary conditions, then the self-weight, and I press save. Then I click on new. I name it as nails. Here you just activate the nails and press save. So close. Then we close it. We again go to general. For solution type, we choose construction stage. And the title being, let's say CS slope. Okay, sorry for the brief interruption. So in the analysis case setting, we name the title as construction stage or CS slope, and solution type in construction stage, we press OK. And now what we do is, uh, I just go to model, and so actually we have run this model for you or a similar model. So for the results part, we'll discuss directly in that model. So we'll start with the interpretation of the results. So I activate all the mesh sets. I go to results. So for the natural slope, the factor of safety is 1.4. And if I switch off the vectors, So this is the critical slope movement like this. If I switch on the vectors, you will see the direction of the slope movement. This is the horizontal slope movement, the vertical movement, and if we look at strains, they look like this. They are localized on the edge of the slope where the failure surface is located with a factor of safety of 1.4. So similarly, if we go to the reinforced slope, we can see the factor of safety has increased to 1.76 or let's say 1.8. Similarly, if you look at displacements, this is how they're going to look like. So if I switch on the vectors, this is the horizontal displacement, the vertical displacement. And if I want to see the forces on the truss elements, so they are facing a tensile force ranging from 18.4 kilonewton to 395 kilonewtons. So if you want to see the outputs or export the outputs, you can just go click on image file. Let's say I want to see this output in the Word format. So I go to Word format. I just click on displacements, total translation, TX and TY, and I press execute. So if I open Microsoft Word now, this is how they will look like, the exports. So if I close it down now, you can also export them as images. Let's say I want to export this image. I just press execute. And if I go on and open up my parent folder, this is how the image exports will look like. So this is how you can just do this simple slope stability analysis for a natural slope and a reinforced slope. So now I will come down to the task that will be used as the or that will be the certification task, and then we will slowly move towards the Q&A session. So for the certification task, this is a model that you have to replicate. So this is again the very simple model. So with the foundation soil, the embankment, and the geogrid as the reinforcement. So for the certification task, I'll just share the PPT with you so that it's easier for all. The submission date is 26th Feb. And as I mentioned before, all of you will be provided with the trial license for GTS NX for 15 days. And all you need to do is just create and replicate the same model and submit them in a format that will be shown shortly. So this is the geometric design. These are the points which you will need to use to create your own create this geometry as shown, and this will be the input material properties. Now apart from this, we also created a tutorial for this particular task, so you can also follow this tutorial. And this will be again shared along with the PPT and the task files. So you need not need to worry if you get stuck. Just follow this tutorial. The same process that I showed follows in here. Instead of creating lines right away directly in here, all you need to do is just create points first. So these are the points. We have mentioned how to make the points. Then just create the lines to join them. And in this particular page, the points that were mentioned or shown before, these are the points. You just need to join them as shown in this picture. And then you can go to meshing, then loading, then creating the analysis set conditions. So also you need to do is align the element coordinate systems as indicated in here. Define your analysis cases, and then the slope factor safety results like this. And please don't worry if your result exactly doesn't match the result of this particular tutorial. There can be a minor changes and it's fine. As long as there is a 10% gap, it's all good, not a problem. So the certification task will require all of you to generate the model as shown in the tutorial, and also write a short summary of the model creation and the results. And this Word file is where will be shared with you. So here you enter your name, your company name, your organization name, and the city and your email ID. Then here on the mesh generation screenshot, you need to attach the screenshot of your finished model after you have done the meshing. That means the screenshot of exactly this one. So you have to zoom it and then send the snip of this particular page. And in the result checking screenshot, you have to send the total translation from the SRM stage. And then for the summary, you have to uh, input or put the snip of the vertical displacements, the lateral displacements, and the maximum axial forces acting on the geogrid. And finally, the factor of safety with and without the geogrid. So I hope the certification task will be clear for all of you. And again, with that, we will share material files as well as the tutorial files. So they will be very beneficial for all of you to easily accomplish the task. If you still run into problems, then we will definitely let you know on how to. You can contact us on globalsupport.midasuser.com. So meanwhile, if you have any questions, please feel free to ask. I'll be very happy to acknowledge them. So I got a question about how do you initialize the in situ stress. At this particular model, we have not initialized any in situ stresses. Instead, we directly conducted the SRM analysis. If you want to do it, what you need to do is just just create a case like this, a construction stage case, if you want. And in the analysis control part, Go to this initial stage for stress analysis, apply KO condition. The KO value is automatically calculated by the friction angle or by the Poisson's ratio, depending on two methods. If you have your manual value, you can also input that. Yes, you'll get the installation guide and the tutorial info on your mails. Yes, Igor. The boundary conditions are very easy to assign for a model this simple. All you need to do is just go to static slope analysis, go to constraint, and for this auto constraint will work. Just press OK. See, like this. Roller boundaries, and here fixed boundaries. Okay, I'll show it once again. Unfortunately, my screen froze, so I'll just show it to you one more time. So for that, all you need to do is go to constraint, auto, and just press OK. So you can see roller bound is on the side, fixed on the bottom. Um, so let's see if there's any other question. So a question asked by Lorenzo is that the element alignment is not something required in all FE software. It is actually it is not required in all FE software, but if you need to have accurate results for the forces acting on the structural elements, then you need to have them aligned. Normally, this also is required in other softwares too, depending on what kind of accuracy you are looking for. I got a question from Sheikh Abdul that why do we use 1D for nail unlike 2D for soil and foundation? See, that is because nail, when we take a plane strain model or a 2D model, it essentially means only one thing. That means the model is infinitely long in that direction, on the longitudinal direction. So the soil, that can be true for the soil and the foundation, but the nail cannot be infinitely long. That's why we take it as the 1D structural element. The deadline for submission is 26th of Feb. That will be written in the PPT that we'll be getting. Alessandro, you can insert the spacing manually when you define the anchor or the nail properties, like here. It depends on you. No problem. So, any other questions? Mr. Harsh, yes, you can design a nail with the grout. Or for that, you can go directly with the anchor modeling that we have. So the starting location being like this. Angle, let's say minus 19. So here you just define your ungrouted and your grouted length. And if you want, you can also put pre-stress in there. It can be done here right away. Tino, actually, we have provided the tutorial file for doing this assignment. So please don't worry about it. Just follow the tutorial file. That will be enough to guide you for this particular submission. We will not ask you anything tough or anything beyond the scope of the tutorial or what has been discussed here right away. So you need not need to worry about it. Please just focus on the tutorial, and you'll also get the video. That will be enough for you to go ahead with the model, with the report submission. Lorenzo, yes, you can modify it right away. I'll just show you this. You can see the nails like this, right? So if I switch off the mesh and if I switch on the solid, can you see the solids now? So this is a extrusion from 2D to 3D. So if I deactivate it and I deactivate the meshes, right, and if I go to front view and I hide it. So all you need to do is that just go to geometry and just make face, apply, apply. So now just go to extrude, select both the faces, direction here. Let's say my length is 100 meters. Okay. So this is how you can convert from 2D to 3D right away. And but when you do that, you also have to remember if you are doing a 3D analysis, you have to go to analysis, settings, go to 3D and put the gravity direction as Y, and it should be fine. Uh, Hi, we have a question for, please understand we cannot answer any questions pertaining to codes. So if anybody has doubt about this 2D to 3D, like as I mentioned in the start right away that in GTS you can do both 2D and 3D in the same platform. So you don't need to worry about it. Just remember that you have to change the analysis setting from 2D to 3D afterwards. So I hope everyone enjoyed today's session.